Okay, everybody, we're getting started here. So if you guys could keep it down a little bit as we start our next presentation. This is one you don't want to miss anyway. So we've got Dr. Leigh here from the University of Wisconsin. He's with the Cooperative Institute for Meteorological Satellite Studies. So he works with a lot of visualization techniques, so you can actually get up close and see what severe weather looks like without actually having to be there. This gets modeled in computers that are a little faster than the PC you probably have on your desk at home or your laptop. But because of that, really this gives you a chance to understand how severe weather operates, and you get a chance to see it up close. So Leigh, I'll turn it over to you. Would you like the...
I'll hold it. That's great. Thank you, Gary, and thanks for everyone coming out here. This is my 4th Dark Skies seminar. This is the best turnout ever. So thanks for coming up, and it's nice to see some familiar faces as well. So I want to first talk about where I fit in within the context of all this exciting weather stuff. As far as I'm concerned, the folks you've already heard, they're doing the hard work. I have the easy job. I get to sit in a climate-controlled room and play with supercomputers, and that's kind of what jazzes me. That's what my approach with this weather problem is to take any supercomputer that I can get my hands on and try to sort of wrestle it into submission to do interesting things so we can learn about the weather. So I'm specifically looking at tornadoes and supercell thunderstorms. So I won't make any assumptions here, but the supercells are the ones that produce the most damaging tornadoes, okay? So those are the ones you see with a nice hook echo, and you can't always warn when you see a supercell hook echo. It doesn't mean there's a tornado. If that was as easy as it was, we could all go home. But the truth is, only a very small fraction of supercell thunderstorms produce tornadoes, about 1 in 4, 1 in 5, but only a tiny fraction of that 20% produce EF4 and EF5 tornadoes. These are the strongest tornadoes that just do immeasurable damage. So I'm trying to understand, using a very sophisticated model under idealized conditions, just what goes on inside of these supercells. So I'm just trying to, building a little virtual lab to study with the world's most powerful microscope, if you want to think of that analogy, to just look really closely at what's going on inside of supercell thunderstorms. Because there's a lot of information we just don't know. Now you heard Louis Uccellini just talk about all the wonderful things, and not all wonderful, some of it's kind of trial and error and trying to get into the right spot, but the Weather Act of 2017 basically gives us the charge to predict tornadoes beyond an hour in advance. I mean, Congress actually passed this, if you can believe it. They passed something, and this is good, okay? This is helping to guide the Weather Service. No, again, I'm not in that loop, really. I am in the pure science loop, but I like to see that language there because it's a call to people like me to sort of, okay, we really need to dial up what we're learning about supercells because we can't do that yet, not even close. How much of the predictability issue is unwinnable? Like how much internal variability is inside of these supercells? How much of it's chaotic? You know, that's an unanswered question at this point. Are there flow features we can identify in some of these storms that are consistent so that we can see something on radar and have a better idea of what's going to happen? The way we do things in meteorology, we have observations, we have theory, and we have simulation. One of the reasons I love this field is I can go outside and go see a tornado, see a storm, study it, scan it. I can look at the equations that define the fluid dynamics. I can simulate it. All 3 of those things. I'm a science geek at heart. I love astronomy. I love astrophysics. I could have been an astrophysics guy maybe, but I can't go to a black hole. Look at how much work it took just to take a picture of one, for crying out loud. So anyway, but this is sort of our field, and it's a wonderful field. And all 3 aspects are extremely important. So the limitations of the current approaches of radar can't, as Louis said, radar can't see tornadoes. You'd have to be close to a tornado with a special kind of radar to really see the tornadic flow. We can see the mesocyclone's circulation, and that can help us to understand how strong the mesocyclone is. That's the updraft that rotates inside of the supercell. But the tornado itself is harder to see. Theory is only as good as the assumptions going into the equations you're using. Any theoretician who's trying to forecast the weather has to make assumptions in order for their equations to be solvable. And the truth is models sort of draw upon those same equations with maybe some more assumptions built in. But each of these areas has limitations. And my approach is to take a brute force approach to the modeling side of things. So I am trying, again, as I said earlier, I'm trying to use the world's most powerful supercomputers to simulate thunderstorms at very high resolution because tornadoes are small and the supercells are big. But you have to sort of simulate them all equally. I believe you need to simulate the entire structure at very fine resolution to capture the right flow features that are important to tornado genesis and maintenance. So, there's some other questions about, how much grid spacing do you need? How much of a supercomputer do you need? The point I'm trying to get at here is, if you're into weather and you are just into the weather itself, that's great. But if you're into computers, that makes you much more useful, and also will make you more able to understand what's going on, because much of weather lives in the computer these days. Lots of forecast models and other issues. But it's not for everyone, but it's a lot of fun when you can get it to work. So I'm not the only one who's done this. I'm building upon a huge mountain of other people's work before me. Bob Wilhelmsen, who I've worked with very closely for many years, he was one of the first to really take a supercell and simulate it and then visualize it. And this took like an army of, it took a lot of time and a lot of effort, because this was back in the late 80s when we didn't have the computing technology. They had to hire graphical experts to put that movie together. One of Bob Wilhelmsen's graduate students, Bruce Leigh, he did a 3-paper sequence on non-supercell tornadoes, because we saw some examples of that earlier with the squall line tornadoes. Going on, some work with Ming Shui at the University of Oklahoma. He simulated probably the first real EF5 tornado. They gave him the Pittsburgh Supercomputing Center for like a week, and he managed to do something interesting. Some other work like that. There's work going on in China now. We have some Chinese researchers publishing research very similar to what I'm doing, using the CM1 model to simulate tornadoes, and that's a tornado that occurred in China. So it's a really exciting time right now. I certainly agree with Dr. Uccellini that we're in an exciting time now, but I think it's more exciting because of the computing technology. The fact that right now you can basically build a little computer, or I would call a little computer, on a desk here, using GPUs and other things that is more powerful than any computer that existed in the 20th century, okay? That's amazing to me. So I do want to do a little bit of sort of geek out stuff here. I recently worked on a review paper on the history of cloud modeling, and it really sort of woke me up to some things. First of all, I'm glad I was born when I was, because I didn't want to have to mess with punch cards and other things like that, but the computers of days gone by were much less, they were harder to use, harder to program, a zillion times slower, and again, I don't know how people did it. In the 70s and 80s, Cray dominated the landscape. Cray came up with a processor that was called a vector processor. It could do multiple mathematical operations at once. Cray was set up, Seymour Cray actually worked for CDC. He then decided to spin off his own company, and he decided to do it in Chippewa Falls, Wisconsin. What is Chippewa Falls, Wisconsin known for? Thank you. That's me with Jake Leinenkugel. So this is me in 1986. I happened to be at the visitor center for reasons that aren't important, and I thought Jake Leinenkugel was just a marketing tool. I thought he was just this guy. I am Jake Leinenkugel. Blah, blah. So we're in the visitor center, and I mentioned to the woman behind the desk about Jake. I made a joke about Jake, and she said, "Oh, he's in the back just doing some paperwork. Do you want him to come out?" And like, he's a real guy. So there's my new Leigh shirt I just bought, and there's me and Jake. So, beer and supercomputers. What more is there? Anyway, so that was. I wanted to even go back further in my life, because one incident, since we're talking about things that like influenced us early on, I was born in Massachusetts. All these East Coasters, Anyway, I was born in Springfield, Massachusetts, Western Mass, and I bopped around a bit in my youth. A little bit after my 11th birthday, this tornado, the Windsor Locks tornado of 3 October 79, traveled from south to north along the Connecticut River Valley. And this is Connecticut in October, and you have an F4 tornado. This is off the charts weird, okay? Supercell tornado. Going north, it destroyed a whole bunch of aircraft at the Bradley International Airport. So it's to this day, I think it's like the 10th most expensive tornado that has ever occurred in the United States. I put a little dot where my house was in Feeding Hills, Massachusetts. And so it crosses the Connecticut-Massachusetts border. So I remember this event. I'm in my house. I just came home from school. The wind starts picking up. I had one of those barometer, hygrometer, thermometer doodads. Of course, I had it in the windowsill because I didn't really understand yet that I wanted to measure pressure. This was before the tornado, but I thought you had to be outside to measure pressure. I hadn't quite gotten my meteorological education yet. But anyway, I remember running to shut windows in the house, watching trees all bending over, we were in the downburst portion of this supercell. So Ted Fujita, a world-famous meteorologist who pioneered a lot of work, he analyzed this storm, and it turns out that this thing was dropping tornado, a nice F4 tornado, and downburst, downburst, downburst. So that impacted me quite a bit. And a few years earlier, our house had been hit by lightning, so I thought weather was trying to kill me. Maybe I should probably learn what's going on so I can protect myself, I guess. So I'm going to simulate my way into a safety. I don't know. So as time has gone on, I got very interested in computers, as will be pretty clear. So I had this dual interest of computers and severe weather. And when I learned from my advisor and his TA, Jerry Straka, who was a professor at OU, that computers and weather and simulation are a good combination, I was set. I knew what I wanted to do for the rest of my life. And it turns out I'm still doing it, so it's kind of cool. Again, so this is just kind of some stuff saying how the computing has gotten more complex. It gets more and more difficult to actually use these computers. So I'll skip over some of this stuff. I'll give you a little bit of my background, but I've been working on this problem for about a decade now. I've been using a specific set of environmental conditions that works, and we get a very nice tornado. And this research is kind of breakthrough in the sense that nobody's managed to simulate a supercell at very high resolution and capture pretty much everything that's going on at very high fidelity. So that's what makes this work significant. So I'm going to show you some of this graphics. We are simulating, this is just to talk about how much power are we using here. 30-meter grid spacing, so you can think of like 30 yards in a football field. If you can imagine cubes with 30-yard or 30-meter axes, that's kind of how we're breaking the world down. I'd like to get that down to even smaller numbers so we can capture more things. So that's one of the things I'm working on. The real storm that I'm going to show you, or the real storm that I'm trying to simulate, actually did produce an EF5 tornado. That's one of the reasons why we're trying to study this event, because we can compare our simulation data to the actual event. I found some of this isn't really that important. It talks about the sensitivity to the initial conditions. I've run this simulation many times, and sometimes I don't get a tornado. And the interesting thing about that, it's not that the model's broken or that I'm doing something fundamentally wrong. It's that there's this underlying sensitivity that we've known about for many years. A highly nonlinear systems such as the atmosphere, you can go down different paths, sort of like that saddle point that was talked about earlier in a sense, right? You could go one way or another. That's sort of a manifestation of that. But I'm hoping to turn this around into an advantage. We've also managed to simulate, as of like a year ago, a new EF5, EF4 that's just like the Tuscaloosa event, which is cool. Now we have 2 storms to study. Okay, so that's great. I'm going to show you some observations first. One of the things we've discovered in our simulations is a feature that occurs in the cold pool of the storm. That's the part of the storm where all the rain and hail is falling, rain is evaporating, hail is melting. It cools the air. That cold air sort of scoots out underneath the warmer air, and it interacts with the inflow in very interesting ways. The feature we call the streamlined vorticity current, or SVC. I'll be referring to that a little bit later. But first, let's get our bearings here. Let's compare. Let's see what a real storm looks like and see if we can sort of compare what we see in the model. So this is a real storm taken. You'll see most of the real footage I have here is taken by Hank Shima, who's Pecos Hank on YouTube. He's a guy I collaborate with. He's a wonderful videographer and an awesome storm chaser. Here is one of his sort of descriptions of a supercell. The inflow band tail cloud region is where we are seeing very interesting features that we think are important to forming tornadoes and maintaining them. Here is a real storm. Oops, I didn't have the annotations there I wanted, but that was a real storm, and this is a simulated storm. And you can obviously tell that one is real and one is not. But you can see here are the different features. When we talk about the different regions of a supercell, there's some sort of jargon you have to get used to. There's the forward flank. It's called that because the storm is moving towards that direction, the forward of the storm. The rear flank, that's where the storm has been. This is a region where historically we've spent an awful lot of time trying to see if signals in the rear flank can help us learn about what's going on with a tornado. And one of the most important results of the research that I'm doing is that it doesn't look like the rear flank has much to do with what goes on with the tornado in our simulations. There's other things going on. So here's some wonderful GOES 16 imagery. GOES 16, I was very much on pins and needles when it was launching. I'm like, please don't blow up on the launch pad. And now, well, yeah, I mean, that's the way it is for all these things. But look at this wonderful imagery, high resolution, high temporal. You can see the visible imagery. These are supercells popping up along a dry line or a squall line. I don't remember the actual event. We computer people don't actually, well, I am bad with events, but this is a nice, shows the fidelity of the GOES 16 data. Here are some loops, again, showing you, we're going to be looking at the tail cloud region and behind the storm and the forward flank. So this, when I show you loops of simulated data, this is kind of what the real world is looking like. And it's important to me to compare what's going on in the real world to what's going on in the model, because we modeling types can get a little too wrapped up in our models. So if something like this isn't happening in our simulation, then we're probably doing it wrong, but it turns out I think we're doing it right. So these are another couple of storms showing tornado genesis, the process of which the tornado forms, which is very important to meteorologists. But just kind of see it over and over again, get that sort of, you see the wraparound of the wall cloud, you can see this tail cloud. It looks like there's like some rotation, lots of rotation going on. So these things are very important, and we're going to be comparing these to simulation data. So here is the view of the simulated storm that I did, the first simulation I did. There's the size of the domain. About 2 billion grid zones, which sounds like a lot, and it actually is. But I can blow these off I can do like 2 of these a day now on Blue Waters, a supercomputer that I'm using. By the way, thanks NSF, seriously. The National Science Foundation, without the National Science Foundation, none of this would be possible. So anyway, the mesocyclone, the simulated storm, rear flank, forward flank, you're getting the picture here. It looks like we're capturing some of those things. This is a really neat sequence that David Bach at the National Center, NCSA, put together. He took my data and he rendered it using a very nice renderer. You can sort of take a look underneath the storm, look at the Madison clouds. You can see the tornado. This one really features well the cloud field. He's done a really good job of capturing a lot of the turbulent flow and a lot of the things that are at very high resolution that actually look a lot like the real atmosphere. And I hope that comes back. Oh, there we go. Okay, so I was throwing together some extra stuff just before my talk, but this is a long sequence showing the evolution of a storm where a tornado is going to form. So keep your eyes right about here in this region of the storm. Rear flank, forward flank. I've painted the surface with buoyancy, so blue is dense or cold, yellow and reds are warm. Believe it or not, there's a lot of warm air in the cold pool, which doesn't seem to make any sense, but it's actually kind of intriguing. This is the rear flank, so this is rain and hail. You can see this thing kind of building up. You're starting to see sort of the beginnings of a wall cloud sort of functioning. You can see some of these little guys coming in from the right to the left. Is that important? Oh, look at it, it's a funnel cloud, it's a funnel cloud. It's a tornado on the ground. The tornado was actually on the ground before you saw the condensation funnel hit the ground, and that's another very important thing to realize. You don't always see a condensation funnel on the ground when there's a tornado on the ground. The air can be too dry, sometimes you'll see debris, but there's a tornado there. So don't always rely on the fact that there's a nice big fat wedge, because there's not always a big fat wedge. Interestingly enough, so this tornado's just doing its thing. You see all these really sort of angry downdrafts in the rear flank. They seem to me to be sort of secondary. They kind of blast out and they kind of go off there. There's sort of an unanswered question about what really supports tornadoes and what really causes them. And as you'll see later on, much of what seems to be going on is that the air that the storm is eating is helping it be really strong, and it's coming from the forward side, not the rear side. So you can see this thing undergoes all sorts of morphological changes. It becomes rain-wrapped. You can see there's multiple vortices. I mean, this is encouraging, because if we can get this right, this is the first step, in my mind, or one of the first steps, there's been a lot of steps before it, to actually nailing the forecast problem. But this is the stuff you can't see. This is vorticity. Vorticity magnitude shaded by the vertical component. What that gobbledygook means is if it's red, it's rotating this way. If it's blue, it's rotating this way. Okay? And if it's horizontal, it's just rotating on its stomach, and I know I'm not going on the ground and doing that. So as you see what's going on here, this thing's starting to get tighter. You can see that there's this gray going to red. That means vorticity is being tilted. That's a very important concept in meteorology, taking something that's rolling like this and having it go like this. That's called vorticity tilting. But it's also being stretched. There's a tornado that just kind of decides to form in there. I'm speeding it up for the sake of time. The SVC, or streamwise vorticity current, we think it's important because it turns out this bundle of vorticity is helping to lower the pressure near the ground. If you can lower the pressure near the ground, you can get a stronger updraft to sort of fill in that void. That's like sort of the basic theory of what we think is important. Because if you can stretch the air near the ground, you can support a tornado. Theoretically, stretching the vertical gradient of the updraft speed is extremely important. So, I mean, the nice thing about the simulation as well is it just goes on and on and on and on. So we've got plenty of times to study here. This is another one of my favorite animations I've made that shows the streamlined vorticity current and shows that this air is indeed kind of rotating and going along. Its rotation and velocity are along the same axis, so it's what we call helical flow, sort of like a barber shop. Does anyone ever have those anymore? Those barber store. I can't even say the word. Thank you, barber pole. All right. Anyway, she goes round and round and round. So this is sort of what you're seeing here is the result of a lot of computing. There's many simulations I've done that you're not going to see, and that's also something that's interesting in our field. For people like me who do a lot of numerical work, you often put aside or toss out a lot of your simulations, and I think, in fact, we should look at the ones that didn't do what we wanted them to do even more to get a better idea of the full spectrum of possibilities in these storms. So I've managed to save data very frequently. In fact, you're going to see every single model time step here. Focus on these little tubes that they're tilted horizontally, and then they get pulled upwards by the updraft over like a kilometer's distance. That is a big deal. I mean, I don't think people realized how strong the updrafts can be in these storms. Assuming the model's right, I've shown you a lot of evidence that it looks pretty good. We've compared it to actual observations, and now there's a tornado that's going to form in that mess. What's happening as you see these vortices all get kind of sharp and very linear. That's the updraft getting super strong, and it just manages to stretch the crud out of some vorticity near the ground, and it all comes together. It's like there's a giant vacuum cleaner at about 2 kilometers above the ground, and somebody puts it on high and then turbo mode. When you hit turbo mode, the tornado kind of falls out of that. It's pretty much a gradual process. It's a consolidation process. It's a strengthening process. It's very steady. Unfortunately for operations, I don't see a trigger because operations wants a trigger. Operations wants to see a signal on radar that's going to give us an extra couple of minutes of warning, or maybe give us an idea of what kind of storm is about to form. But maybe we can pick up something like the SVC. Here's all these vortices just sort of coming together. It's like there's a big vortex convention, and they all just kind of merge into one. Again, the updraft is getting super strong at this point, and it's essentially just drawing that vorticity together, and the tornado just sort of comes out of that. It's a very gradual process, and it's one that I think this mode of tornado formation hasn't really been seen before, or at least not been identified like this. So we're going to study a lot of this to figure out what's going on. One more view of this event. I'm showing the cloud base so you can see what the cloud would look like. All the vorticities kind of coming together. You get this parade of vortices, as I call it, coming from the forward flank. These guys some of them are rotating cyclonically, some are anticyclonic, but most of them are cyclonic, and they all just kind of build vorticity into that vortex that then becomes a tornado. And you'll see, notice I said there's no tornado on the ground, and there might be a tornado on the ground with no condensation funnel, and you'll notice that the vorticity was there before the cloud made it on the ground. Okay, I'll take a breath. I do actually breathe, believe it or not. So there's this sort of question about, is tornado genesis a top-down or bottom-up process? This has been sort of, you might have seen something like this in the news lately, in science news, so it's kind of news. It's the news I read anyway. So I'm just going to show you this. This is the process of the tornado becoming a tornado over a very short time period. That's what I'm calling tornado genesis. Some people extend it even further back, but keep your eye on these. These are vortices, so they're spinning, but if they're black like that, that means they're not spinning very fast. If they're white and red, that means they're spinning fast. So I'm going to run through this twice. So first, let's just watch this, and I'll take a sip of water, and then we'll go over it again. All right, that's tornado genesis. Any questions? No, just kidding. So let's watch that again. All right, so what you saw was, it looked like things started from the ground, and that's not a tornado, okay, because it's not rotating fast enough, but it's a vortex. And it's the vortex that's going to become a tornado. So it's not a tornado, but now you have tornado strength winds aloft. It's still not a tornado because you have to have the winds on the ground to be a tornado. And then you'll see over time it becomes a tornado. So is tornado genesis a top-down or a bottom-up process? Yeah. And it's also a side-by-side process, so it looks like there's a lot of those things going on. Because what I'm not showing you are those little vortex mergers because I wanted to choose a value of vorticity that showed that tornado forming. So it's complex, I guess is what I'm saying. Here's the thing that really strikes me. If you'll watch this early phase, about 15 minutes before the tornado forms, you see all these vortices taking a little trip from the forward flank to the rear flank of the storm. And they just kind of keep going, and they keep going, and they keep going. But the pressure is starting to drop up here. So the pressure gradient is getting larger, and you'll start to see these guys start to sort of slow down and then start make a trip around and then tornado. So what's up with that? There was no surge in the rear flank that started that tornado. That's our leading theory right now. It looked more like a very gradual process. And this thing right here, the streamwise vorticity current, and I'll show you this in a little bit, and we have to do this quantitatively, but it is definitely associated with a very strong pressure drop. And again, the pressure gradient force is what makes everything move, makes the wind move fast. The pressure in the center of a tornado here is about 150 millibars, or 150 hectopascals below the air around it. That's like almost 2/10 of an atmosphere. It's just huge pressure drops. And now this thing just goes ballistic. It takes on a two-celled form. This is when it's like doing EF5 steady damage for like 20 minutes. I mean, it's just crazy. Here I slow things down, and we can look at the same thing during the mature stages of a tornado. You can see these gray vortices are horizontally oriented, and you can just see how they're being tilted and into the updraft. So you've got horizontal vorticity, which is just doing its thing here, that's very quickly being translated into vertical vorticity, and that's spin about a vertical axis. And you'd think that things that spin on the vertical axis might affect the tornado. You'd probably be right, because what is a tornado, right? It's something that spins very rapidly about a vertical axis. So this detail is pretty exciting. No one's managed to do this before we did, at least with all this fidelity. And we're just going to keep pushing it. I've got a simulation on the Blue Water supercomputer right now. It's going to take over a month of all the machine just to do. We're just pushing it as hard as we can, not just for fun, but because we need to. Somebody needs to be on the leading edge of that curve to see what's going to happen when this gets to operations. I mean, eventually stuff like this could be done in operations where we have maybe, I won't even make a guess, but it could be we could have a whole suite of simulations done before the storm forms to inform us on our decisions, which is the whole point that's been made multiple times. So this is a higher resolution simulation of this storm. We see the anticyclonic tornado that kind of comes and goes. I've seen that one a lot. Then the cyclonic tornado forms here, and this is the EF5. You'll notice this looks a bit different than some of the other stuff I've shown already. The clouds in the tail cloud are more convective, more cellular. They're not as laminar as before. But it's a beautiful storm. You see all sorts of very intricate vortex action, you might say. You can see that there's a lot of things showing up in the cloud field that show that suggest strong rotation, just like you see in the atmosphere. There's plenty of footage out there of tornadoes on YouTube, and you'll see some of these horizontal, like smoke rings, kind of going around the tornado. We get those in our simulations as well. That's horizontal vorticity that's being stretched, and it's able to, if it's humid enough, the conditions are just right, it'll show up in the cloud field. And then there's another guy that decides to just form out of nowhere. That's anticyclonic. Then they do a little dance. I showed this last year, but it's still worth showing again, right? I mean, it's so cool. And it's just, I don't know what's going on, but we've got plenty of data, and we'll be analyzing this as well. And here is the vorticity field. There's your anticyclonic blue guy, and the blue guy kind of goes away just as you see the red guy start. So there could be some very interesting, there's a saddle point for you. You go from the anticyclonic side and you jump over to the long track EF5, and here it is again. You often see a lot of anticyclonic vorticity in the rear flank. I've noticed, I don't know how significant that is, but there's this sort of, I don't know what you call it, process going on, but just as that guy decays, our tornado forms here. And yes, you can see just the upward motion of this red stuff. The updraft is ridiculously strong. And if there's one thing that I've been trying to sort of suggest to the community that does the actual hard work of measuring storms is there a way we can measure the updraft? Not just downdrafts and not just horizontal winds, but can we measure the updraft? Because I think that's where most of the important things are going on, is in the updraft. Here's another view of that same thing showing the SVC rotating. You can see that rotation and then the tilting and then going into the mesocyclone. So plenty of detail here. So another approach, because there's so much detail, I've decided to take out some of the detail by doing some averaging. but I'm going to average in time. Okay, so I'm going to take, when you see every single slide you see in this sequence is 121 times being averaged. I take a centered window or a moving window average, but I go 60 points to the left, 60 points to the, or forward, backwards, and average them together. So you take out a lot of the noise, and you can look at, take out the trees and look at the forest. So here we have pressure deficit. So when you see these isosurfaces as low pressure, this is the updraft speed. So the outer contour is 30 meters per second. On the right, the outer contour is 15 millibars below atmosphere, or 15 millibars lower than the surrounding air at that height. And what you'll see is a gradual strengthening process. You see this feature that gets, the pressure drop gets larger and larger. The same time the updraft is coming lower and lower to the ground. You see those isosurfaces going on, and eventually it gets strong enough, and I wouldn't take this too seriously, but you start to see the tornado form out of the side of this thing, and there's a tornado on the ground. Notice this sort of little protrusion off to the side. That is associated with the streamlined vorticity current. So there's a low pressure drop off the side of a tornado that we think is helping to support the updraft that is then helping to support the tornado. So we want to close the loop on this whole thing. And again, this is sort of, we haven't done all the analysis yet, but I make these movies because they help me decide what to look at. So this really tells me, when you look at this little low pressure thing over here to the side, that's probably important, right? And notice how the updraft comes so close to the ground there. So it's all about what you're feeding this thing, the guy who mentioned he wants to kill tornadoes. If you want to kill a tornado, warm up the cold pool. But I don't mean that literally. Don't like set fire to everything. No, please don't do that. But the truth is, if you actually reduce the buoyancy here, it actually, and you don't see it until later on, but it actually disrupts the tornado. So actually, I'm not being serious. I don't mean we can actually stop tornadoes. But I do think that there are some things that we can learn about them and learn where their weak spots are. Maybe 50 years down the road, there could be some sort of mechanism to disrupt it. But we're way, 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 way beyond or before that at that point. So here's the same sequence showing also the streamlined vorticity. So look at how it's just kind of coming in like crazy. There's your pressure dropping. There's your updraft lowering to the ground. So this pretty much tells the story. This is a story, to me, that is a new story in how you can get a tornado to form and how you can get a tornado to stay on the ground for like an hour. And what's interesting about this simulation is it's the same process. The genesis process where the tornado forms is actually not that interesting. To me, it's what's causing this pressure drop that's interesting that leads to the tornado. Now, eventually we'll get to studying the tornado and the small scale circulations within it, but the truth is I'm more interested in the storm. I was driving to, I guess I was going to Purdue the other day to give a talk, and an analogy popped in my head. In a way, the tornado is like the last chord of A Day in the Life by the Beatles, right? Bung, right, as boring G chord 38 grand pianos. I'm all interested in the cool part before that, like, woke up, got out of bed, dragged a comb across my head. That's what's going on. That's the part of the storm where you're building up to that crescendo to get the tornado. What's going on there? What's going on there? So that's more what I'm interested in, the sort of creating the environment that leads to the tornado. This is streamlined vorticity again. Notice how it goes crazy, and as the colors get darker and darker, that means the wind is moving faster and faster. So we're stretching vorticity, we're tilting vorticity, and somehow there's a feedback mechanism that makes the updraft stronger as it eats this stuff. And that's what we need to really figure out. Okay, so the research side of this is to figure out why this is happening and try to understand it, and then use that as a way to sort of give us insight on how to predict as well. Because really, we're all trying to make these storms easier to understand it before they happen so that we can get people out of the way. Here's the Tuscaloosa storm that we've been simulating. So this is a new one. You haven't seen this before. It looks pretty good. You've got the cascading rain and hail. I've kind of sliced it through a little bit. Here's a tail cloud. There's actually a tornado on the ground at this point. You just see the wall cloud. We have an issue with some of the cloud getting scrubbed by rain because we have some physics we have to fix in the model, but there it is. Look at that. There's the vorticity field for this new storm, the Tuscaloosa one. This storm actually draws a lot of vorticity out of the environment and tilts it. That's on this side, but it also draws it in from the cold pool, and there's your SVC over here. So there's actually an SVC in the second storm, which is, I guess you could say it's gratifying. I mean, from my perspective, because if it's in one storm and another storm, then it's probably in the atmosphere, but we still have to find it. There's efforts to go find it. But there it is. So I'll show you some clearer pictures of genesis on this storm. It's a little different than the other one. We don't have a super strong SVC when the tornado forms, but we do have a strengthening updraft. And you can see that in an upcoming sequence. But as you can tell, there's a lot of detail in these simulations. Again, grid points are 30 meters apart. Here's the genesis portion. I'll pause for just a second. But when you look at operational models like the NAM model, the GFS, those are on like kilometer grid spacing. So they cannot capture this type of flow. They can barely capture the real supercellular type stuff and capture the rotation. So we have a ways to go before this kind of thing can be done operationally, but it's going to happen. It's just a matter of when. So this is prior to tornado genesis for the Tuscaloosa-like storm that we're trying to simulate. Notice there's a hook. That's not a tornado yet, but just watch what happens. It's very like, oh, they just all kind of come together. There's a little bit of a handshake maybe, and then there's a tornado. I mean, it's a very gradual and sort of just, you get enough of that stuff coming together, and it produces a tornado. Here's a longer sequence showing the same thing. So there's no tornado yet, but you've got some enough cyclonic vorticity, and it just kind of all bundles up together and makes its way into this tornado. There was no downdraft that started it, and this one has there's a nice, very thin hook. I kind of sliced it out here, just happened to run into the side of the domain. Remember, when I simulate these storms, I'm only showing you a portion of the full simulation. There's a whole lot more that you're not seeing, but I focus on the tornado because it's what's most interesting, often most interesting. So this vortex, again, I'm showing you every second, maybe even every fraction of a second here. And you can see, these are those things that sometimes show themselves up in the cloud field, those little rings, those smoke rings. You can see them, this vorticity that starts near the ground, it gets caught up in the updraft within the tornado and kind of goes up around it. Some of these anticyclonic blue guys, they don't fare so well, they get tilted, and sometimes they fight with the main tornado. That shows up a lot in the other simulation as well, but you know, it just goes and goes and goes. So there's some more of that generation of horizontal vorticity. Sometimes the tornado actually will sort of burp. I don't know how else to call it, but it's sort of transitioning from a single cell to a 2-cell tornado. That transition period causes these like burps of downdrafts that sometimes create rings that then get lifted. It's fascinating. I mean, it's just absolutely fascinating what I'm seeing in these simulations. So the fact that we have two events where long track EF5 or EF4 tornadoes occurred, we have good, I would say high fidelity simulations, two different events, and we're seeing some things that are similar and some things that are different. That is exciting to a scientist. I mean, if everything looked exactly the same, I would be worried. But there's a lot of significant differences, but there's some sort of fundamental similarities that I'm glad are there because it sort of helps us. It's not completely hopeless and it's not completely all chaos, which sometimes it feels like it is with some of these simulations. And let's see, like this just kind of like you can see this stuff just goes on and on. I guess I got enough time. I won't skip ahead. But yeah, so I have fun making these. I'm always looking for new tools to make stuff like this faster and better. And stay tuned. We're working on. My research team is working on pushing the envelope even further on this work. Again, like I said earlier, I've got a whole pile of machine time that I have to burn up like in 6 to 7 months. And we have to create this data, then we can study it later. It takes years to study storms like this because of the tremendously large amounts of data, as you might imagine. At this point, I think the tornado has exited stage left or right, and it's just kind of moving out of the box. But yeah, here it is. Here's Genesis once again, a bunch of little red guys and a blue guy, and out of that just comes a single vortex. So that's Genesis for that particular storm. So we've got our work cut out for us. Here's another nice view of the SVC forming in the Tuscaloosa storm. It forms a little bit later, so this sort of horizontal vorticity being tilted and then wrapped around the tornado. This is actually later in the simulation. So we have a well-formed SVC in this simulation, not right away, but it kind of comes and goes. So that's intriguing. Who knows what's going on, and we're going to have to study this, but we're going to have to start looking at this in terms of budgets and trying to actually just do the physics right. Here's another view of Tuscaloosa with the tornado forming. So the blue are downdrafts, and this is the same view, or the same scene with two different views. So here's the downdrafts in the rear flank, here's the updraft. You'll see there's vorticity, so it's already forming a tornado. You can see the hook echo in the reflectivity field. But you know, it's a very gradual process. It's a very steady process. It takes time, and the tornado just, you know, does its thing. Once it forms in these simulations, they stay locked in for a long time, and that's one of the points of this research. We are only right now trying to study the most devastating tornadoes. It's not that we don't think the other ones are more important, but these have the highest impact. So let's learn about these first, and then we can start worrying about the whole suite of tornado strengths that come out of supercells and even non-supercells. So again, this thing takes off. Notice the updraft has gotten lower. The tornado's gotten fatter. It's doing its two-celled thing. I'm speeding it up for the sake of time, but it eventually exits stage right, and it's all gone. So I have one more sequence I'd like to share with you. It's comparing simulation data with observations. I've done a little bit of that, but here, again, this is primarily done by Hank Scheima. We put some stuff side by side and just said, hey, let's just do for fun to see if this modeling stuff is doing its job. So here on the left is the rendering. I've changed the color a little bit, but there's some actual cumuliform clouds popping up on the right. It looks pretty good. I got some Madison clouds for you. Which is real, which is fake? It might take you a second, but the one on the left is fake, and modeled. The one on the right is a photograph or video, a sequence of photographs. The tail cloud of the storm that we see in the cloud field in our simulation matches pretty well with what Hank saw in a certain storm. He's got such a huge catalog of storms in his head that he can sort of come and find that stuff, which makes it very useful. And here's something that intriguingly suggests streamlined vorticity-like flow along the forward flank. Notice how those clouds are kind of taking a similar path as the parcels are. And here we just kind of do a little fade, then a side-by-side. I think we're getting it right for the most part. And as the guy who's running the model, I can point out a million flaws, but I can also agree that, hey, we're doing pretty well. You can see multiple vortices here in this. Those are actually just the cloud field being shown there. And here's some of those little clouds, those little manifestations of the horizontal vorticity rings, and you can see similar activity in the simulation, those blue guys and those red guys when they get tilted on their side. It's pretty compelling. So I guess that's most of my talk. I guess to close, I will say, and I haven't talked a whole lot about technology, but it blows my mind where we are right now. We are in a revolution of several different revolutions apparently, but one is a GPU or graphical processor unit revolution. Those are the things in your PC or graphics card, only they're now on steroids, and you can do actual science with them, and you can do really good graphics with them. It's hard to do this. I spent about 10 years getting this stuff worked out to where I could actually have the simulation, but I'm going to be sharing, I'll be giving back to the community once I get to it, so that everybody else can use this code and everybody else can run these models as well. I do think we'll be doing 50 member ensembles at 30 meters, so 50 simulations instead of one, and then do statistics on that. That's going to really help us to answer some of these tough questions. So I think that's all I got. Oh, I do have a few opinions. I do think that the supercell conceptual models we have right now need to be updated. I think the rear flank downdrafts are sporadic and probably more the cause of some of the things going on in the mesocyclone rather than causing anything important. I think if you're looking for an elusive tornado trigger, you're going to go crazy. I don't think it exists. I think it's a process thing that we need to study and understand. I think that one of these little guys along the forward flank coming in, it doesn't matter which one, as long as the updraft is ready for it, you're going to get tornadogenesis, but who knows? I could be wrong. Someone could prove my theory wrong. Nothing would make me happier because that's how science moves forward. I want to acknowledge my collaborators, and again, I want to say the National Science Foundation, it funds the Blue Waters Machine along with the University of Illinois. I have some NSF grants to support myself and my graduate students and some of my collaborators. They're all listed here, and for the sake of time, I'll just take some questions. Thank you for your time.
Time for a real quick question? Yes.
If you looked at, and I'm sure you have because I'm an old guy with all other knowledge, the cold pool or the inflow interacting, does that have anything in your mind to do with changing the horizontal flow?
Can I see that? When you have cold air adjacent to warm air, there's a density difference that causes some circulation. That's what's called baroclinically generated horizontal vorticity. It's quite a mouthful. But that, just having those two things side by side will induce circulation. That produces horizontal vorticity. So yes, along those boundaries is where you see a lot of that, as you've seen in some of these animations, like right along that forward flank. Not only is it buoyancy driven, but there's also dynamic pressure forces going on. It's like when you suck on a Coke bottle and the pressure goes down. You know, there's dynamic pressure changes, not just due to warm or cold, because pressure and temperature and density are all interrelated. So yeah, that region of the storm along the forward flank is, I think, crucial, and that's where we're seeing our SVC, the parade of vortices and all that. I think that's the part of the storm where, for process-wise, where we should be focusing on to understand the strengthening of the meso that leads to the tornado and then supports the tornado. But I could be wrong.
Is that what we always have to say?
No, but yeah, I mean.
Okay, well, Leigh, thank you very much.
Yeah,
Appreciate
sure.
it. Are you going to be around for a little bit?
A little bit, yeah.
Please stop by and see him.